gonna write something on the blackboard. Figure it out. What's this about? I think everybody is just to recap what we did last time because there was a mistake. So actually, it was not a real. It was a mistake. Yeah, that's understandable. Yes. Well, this is nothing new, so we're cool. Okay, here we go. 5 minutes of this. But yeah, so I want to just recap like the basic, like last time we saw cases of matrices that were not symmetric and so had a dynamics that was not converging. So this is the example we saw last time with the 1 and -1 as weights. So with this matrix, remember that 1, 2 is the one that goes from 1 to 2, and the 2, 1 is the one that goes from 2 to 1, adding the perceptor degradation. And the update works in the following way because we have 0 in the other one. And remember that we had proposed excitations things. And so the excitation of the left layer was defined in this way in a bound, and the excitation of the right layer was defined in this way in a bound. And see that the index is the first one for the right layer and the left one. In the Hopfield case, of course, they are the same because we saw that if it's not symmetric, it doesn't converge. So we need symmetry. But so if you want to interpret this using the excitation, what I want to say is that this is SGN you want of V1 because of this order of and this is sorry 1, yes. And this is SGN somehow G2. You want to interpret this update as a bound. You want a link between the two. This is what we saw last time. So we saw a case very simple with 1s and -1, and we saw that the dynamics was this. And doesn't converge because you can either stay here randomly or you can move and you never stay somewhere and there is no place, there is no state where you end up there and you never come out. You can always move. But on the slides, I put this picture that is the one in the Rojas book that is a different network because it has different waves. And so this is the dynamics of this network, which is slightly different. I forgot one index, probably. No, otherwise this would be a stable state. Exactly. Okay. So this is not I put this on the slides, but whatever I said on the blackboard was this. So I corrected the slides, now it's good like this, and someone got points because it spotted the mistakes. So please spot mistakes if you find them. But so if you try to write the dynamics of this one, this by dynamics I mean this, how the network transitions and which are the stable states. You can do the same with this network, which has like opposite sign. And you can see that the dynamics is different because I stay here with x1 and I stay here with x2, for example. But of course, they're isomorphic, like there is a way from passing from one to the other. They have the same amount of stable states. Actually, they have the same, like, they don't have the same, sorry. If they had stable states and they were isomorphic, there should be a way of sending one stable state to another. If one has one stable state, so another one has two, they are not isomorphic. They don't have the same dynamics because there is no way of like sending two in one. But in this case, what you have is that there is a way of converting one to the other, and is with the transformation that switches x1 and x2. So if you switch those two and you change all the arrows x1 with x2, you obtain this. You can try do the steps before exchange all the tuples and then change all the arrows. And then you will have this on this side, so you will have to mirror it to have exactly this one. But yeah. They have similar dynamics just because it's almost the same matrix, but they are different networks because they have different weights. Anyways, none of those converges because they are not symmetric. I think that's it. I don't know whether I want to say something more. Oh yeah, okay. This is the excitations using the band. Let us recall that in Hopfield network so far we used the states that were -1 and 1 at the power of n for a network that has m units. So one can say that one can use the definition of excitation. We just take the EI because anyways now this is equal to this because which the index is the same. So I define the excitation E of the unit I of my Hopfield network for I that goes from 1 to n. I think I did it anyways, but let's just forget about it. J that goes from 1 to n. Y, G, I. Yij is the same. Xj. And you can also put that j is different from r. Because this is equal to 0. This is called the excitation of the unit type. So whatever comes with the weights from all the other nodes of the network. And so whenever I update, imagine that I update a unit I. So the new, I have the old xi, imagine that my xi prime is the xi updated. I can say that I was telling you that I was using as activation function f theta I, which was the Heaviside stack function, but like tailored for -1 and 1. So this thing is equal to 1 if x is greater than the threshold or equal, and is equal to -1 otherwise. So if theta I is equal to 0, this is the sine function. I'm just repeating. So when I update, what I do, update xi with xi prime. What I do is actually to calculate f theta I. Sorry, let's do for the sine function. Oh, I don't care, let's do it. F theta I of what? Of the xi excitation minus theta I. Sorry, no. This is false. I'm doing f theta I of the EI, or I'm doing this. Those expressions are equivalent. Either I subtract the threshold, either I just apply this. And because here I just put inside this one. This is the way of updating. I pick a random node and I do this. Before I was telling you I do this, but now I'm just telling you this is just the excitation. So it's just a more compact way to write the same thing. We don't care. Just I wanted to specify that. This is important also. Keep that in. So what is going on? Today we're going to talk about again the XOR problem, which is come back. Nice come back. What is going on? Last time I showed you how we could find a Hopfield network that did the OR. An exercise you have already is about doing the AND, the same thing. And I was telling you that we were choosing, so what does it mean, Hopfield network that computes the OR? Because when we did that with, for example, McCulloch or perceptrons, we had input and output. Here, kind of, in those type of machines, you just have a state, and you have the set of stable states, but there's no arrow going out of this machine. Those things just like cook themselves. There is no one that can touch them from the outside. Right? So I introduced the concept of clamped units, that were 2 units that were chosen to be x1 and x2, that were the things that they want to do the OR with. Clamped unit is a unit that I decide I don't update. So whenever I do random updates on my Hopfield network, I just don't do that for those units. And I showed that Hopfield network was computing the OR because the stable states of the network were the lines of the truth table of the OR. So maybe you're writing that. Should I cancel this recap? Is that okay? Is everyone okay? Should I cancel this? So I'm not gonna tell you all what is wrong with XOR again, because we already know what is wrong with XOR. XOR is not a logical function that can be computed with a one single unit of perceptron. So perceptron learning cannot solve this problem. But, so, you saw in the previous time that we had a 3 units Hopfield network that corresponded to a perceptron. So like the inputs and the central node. So here, like the analogous of how, so in perceptrons, one unit, 2 inputs and 1 output. And here we have Hopfield, 3 units. Whereas before it was in the input-output relation that was giving us the computation of the OR. And here it was the set of stable states are the lines of the OR table. We changed the true and false with -1 and 1 instead of 0 and 1 because in Hopfield we have -1s and 1s. We just, yes. But so if we have a problem here, we will have a problem with Hopfield with 3 units because I just told you that, for example, in the OR case, we have this equivalence. So the fact that I cannot find a perceptron that does the OR with XOR with 1 unit implies that I cannot find a Hopfield network with 3 units without XOR. So you can do it with 4 units. I'm not gonna tell you how because it's like on transitions on this case. Kind of like a bit complicated, and also you have to choose the weights. Let's try to understand why it's not doable independently of the relation with the XOR, with the perceptors. So if you try to write the XOR truth table is this one with -1s and 1s. So imagine that I have 3 units. My 3 candidate units are x1, x2, x3, and one of the 3 should be the XOR between the previous 2, kind of. Because I want those lines to be the stable states. So in all the sets of -1, 1 at the power of 3, I want those 4 to be stable states. But you can see also that it's a cool table because whenever I choose 2 columns, the third one will always be the XOR of the 2 that I chose. I have to think about it. But yeah, so since whenever I choose 2, the third one is the XOR, and I have a problem with doing XOR with 2. There is no way I can do it. Like any attempt, any combinatoric attempt that I try leads me to the same problem I had with XOR with a perceptron because it leads me to a perceptron. So that's the reason why I cannot do it. So they say that this is the network that does it. With 4 nodes. This is just like a Hopfield network with 4 units and all the weights written down. And one should find a way of finding the weights. But I'm not going to prove anything about this because in the last part of today's lecture, we proved that for any Hopfield network, there is an equivalent perceptron. And with perceptrons, we know from perceptron learning that we did 2 weeks ago, we know how to find the weights. So if I have an Hopfield network and I want to find the weights such that this gives me the XOR, I will convert it into a big perceptron and then I will apply perceptron learning and find the weights such that they do the right linear separation. So I cannot do that with 3 units, but I can do that with 4. 4 means that I have also an extra coordinate on the things that correspond to the XOR. So if you take the XOR truth table, the first 3 coordinates will be the ones that I want, but I will have an auxiliary coordinate that I will not care about. I will say the stable states that correspond to the XOR are those vectors, this part of the vector, and the rest is auxiliary that helps me to compute it. But yeah, it's reasonable that we cannot do the XOR if Hopfield and the perceptrons are equivalent. That's just what I want to say. But yeah, let's move on. We have to talk about dynamics. Why? By dynamics, I mean those graphs that I described before. Dynamics means I do all the possible transitions since I update randomly x1, x2, x3, whatever. I transition by updating one certain unit. And dynamics means also talking about stable states and what we would call Garden of Eden configuration or something. It's kind of weird stuff, but let's make an example to understand it. I'm not gonna go through all the example, but because I think it's cool if you try it out on your own. But I'm just gonna show you this. So this is an Hopfield network of 3 nodes. I put as thresholds a half, minus a half everywhere. So my activation function is f minus a half. If I'm greater than a half, I will be 1 minus a half. If I'm smaller than minus a half, I will be minus 1. Will I say it right? So I can compute the energy function of this thing. And the energy function all around. The quadratic form of plus an extra term. This was the equation for the energy. X transpose x plus theta x transpose, or the contrary, I don't care. Yeah. And if you do all the computations with the weight matrix, you can write the weight matrix of this machine. This should I write it? No, write down your own. From which goes to where, we write the weight matrix. This number. For going to x1, from x1 to x2, I have -1. x1 to x3, I have 1. And then I have -1 for going to the other. And this is the same. So I can write the energy function, that is this, if you do all the computation. It's a function of 3 variables. We don't cry, just do it. Yes? So one can see what, right? You can perform iterations. So you start from the first node. I'm just gonna do some iterations because it takes a lot of time and you will have an exercise to do this on your own. But yeah, so by dynamics of this network, I mean, I give you a starting vector and I tell me whatever happens. If I tell me what happens, whatever I do. Like, let me see what are all the possible lives of this network if I start here. If I start here and I update x1, if I start here and update x2, 3, x, so on. It's a tree, like whatever. At each node, I have to tell you what happens if I update either x1, either x2, either x3. Yeah. So there's a cool drawing. It tells you that this energy function, the more I proceed in the updates, the more the energy gets low. Not surprising because of the link with the bumps, and in the bumps we said that this is true. So why should it be false here? But yeah, basically the energy is like one falls into local minimum points of local minima for the energy, no matter what happens. That's why Hopfield networks are examples of unsupervised learning. Because I'm not using explicitly the energy function for the updates. The updates are just like what I told you before, are just this. I see whether the sum of the weights coming passes the threshold or not. I'm never using the energy, okay? But this is kind of like a loss function. So I'm like minimizing that. I'm minimizing the error somehow. So it's kind of, because the problem comes from physics, I don't know, but like it's you end up minimizing something that you're not explicitly using. That's the main point. Okay, so let's do that. I just want to show you an example that to make you believe that this actually happens, so that there's more examples on the books as well, and you will have an exercise. So if I start from the point -1, -1, -1, this is called a Garden of Eden configuration, because there is no way I can get here. Either I start from here, either I will never reach this state. You know the sets of state, there is always a subset that is called the Garden of Eden, or the Hopfield network. Garden of Eden is Eden, I don't know, because Adam and Eve were there, just like, they just came there. There's no way of getting there. And then you come to the real world. Yes. Yes. That's the definition. That's when I do all the computations. I'm just gonna write it. this is what happens. So you start from there and you update. You see that from each node there is 3 arrows coming out. I don't know, I can show you the first one, maybe go back to this. So, for example, if I'm here and I update x1, I update x1, so what do I mean? I do the f minus a half of what? Of whatever comes from the others. So 1 times the value of x3, that is -1. And the other one is -1 times the value of x2. So it's -1 times -1. So this is 1, this is 0. F minus a half of 0 passes the threshold because it's bigger. So this is 1. So if I update x1 in this thing, I transition by updating x1 to this other state, 1, -1, -1. I updated x1, so the only thing that changes is 1, because I can change 1 unit at a time. And this has a lower energy, you can prove that. You can prove that by meaning like you calculate the energy function of this vector. You have the energy function, you put the coordinates and you speak a number. The number is lower and it is 1.5, etc. So you update x2. Oh, let's update x3. And you get another vector that is -1, -1, 1. Should I do this? Update x3. I do add -1/2 of what? I update x3 starting from here. So my values of the nodes are all -1s. I update x3. So I take what sigma x1, that is -1 times 1. So it's -1. And I take what comes from x2, that is -1 times -1 weight. So it's 1. So I have again f -1/2 minus a half of 0. That is 1. That's why I transition from this to this by updating x3. What if I update x? Wherever I am, basically I'm asking what happens if I update x1, what happens if I update x2, what happens if I update x3. If for some reason I stay there, for example, if I'm here, and then you have to do it for x2 as well for this. And then if you update x2, you end up down in this vector, like this. The energy. This is if you update x2, that has a lower energy. Whereas, I don't know, you can test that whatever you do here, either you update x1, either you update x2, either you update x3, you obtain the same value. So this is a stable state. And so on, like for every element of the tree, you try the tree updates. Note that this is not the lowest I can get, because if I do all the other options, I end up here with another state that is 1, -1, 1. And this has a lower energy than this, but it's still a stable state. So stable states are local minimum, points of minimum of the energy. They can be minimum of like different points. And in this as well, I don't get out. I can find myself going, like, for example, in this state, I run away if I do x3, x2. I don't remember well, but like that's not obsolete. But if I do x1, I stay here. If it's not a stable state, because I stay here just if I update x1. But if I do x3, x2, I run away. So a stable state is somewhere where I just get stuck there, whatever I do. A Garden of Eden situation configuration, there can be more of those. Is somewhere either I had started there, either I will never go there because there is no arrow going. Yeah, so you can have fun doing all the options, but I'm not gonna do it. But you can see that like the energy, whatever you do, gets lower. So the question is, can we prove that no matter what update in our Hopfield network, then the energy will get lower, and then the algorithm will converge to stable states. Under the assumptions that the matrix is symmetric and has a 0 on the diagonal. Is everything all right so far? Is it trivial or is it too bad? I don't know. I don't know. Is this clear? Actually, to check out all the details, one needs to like to do the computation. Once you have a couple of examples from the book, like this one or another one, and all the arrows, remember that they correspond to the update of a certain unit. That's it. So intuitively, what I want to show you with this is that we converge to stable states, and the energy gets strictly lower whenever I update something. Because if I don't update something, imagine I'm here and I select x1, I stay here. So the energy stays the same. So convergence of Hopfield networks is the same result as we proved for the bands, but here it's a bit trickier, and I'm telling you why later probably. So Hopfield network with n units and asynchronous dynamics that starts from any given state eventually reaches a stable state, that is a local minimum, a local point of minimum for the energy function. So the proof is a bit tricky, but if you look at the proof we did for the proof that we did for the band, it's very similar. It's even easier because we're just axes, we don't have ones. Okay. That's cool. So okay. So we have a state x, x1, xn. And now we network with n units, and this is the energy at point x, at state x, sorry. Is this thing. Yes. Data x. We have thresholds, threshold vector, so means that for every node I have this activation function. Nothing great going on. Do I do all the computations to tell you that this is equal to this, or you believe me? I gave this also the definition, so it's not the. We put all the coordinates inside this thing, and you do all the multiplications to get this. Should I do? So now, I'm telling you, I want to prove that if I do one random update of one node, let's call it xk, I update xk. Just the k coordinate of the vector x. So I call x prime the new vector that is x1 prime, xn prime. That is such that x prime j I is equal to xi for all I depends on k, and xk prime is equal to xk. Just what I'm telling you is that the new vector is the same as the other one, and I change the k coordinate. I'm doing one random update in one node. So the question is, what's the difference between, that's not true. All those are equal, but this is minus x3. I updated it. So what I did was, what do I do when I update? X prime k. I calculate either f theta k and the excitation k. Either I do the sine of excitation k minus theta. So we have to do the break now. So let's move on. Let's continue after the break. We have 10 minutes break because last time I stole 5 minutes. So it's at 1. I had to break it because it was too long to not do. Yeah, it's not a big deal. Maybe we can restart. I don't know. I don't know. It's 10 minutes past. I don't know.
Yeah.
Okay. So it's not a big deal. At the beginning, I told you what excitation was, and I defined it as this, just this, the weighted sum without the threshold. And then I said when I check with the function with the threshold, I do. Oh, sorry. Yes, of the excitation means doing the sine function of the excitation minus the threshold. Okay. But the book defines the excitation with the threshold. So the excitation is the weighted sum minus the threshold because sometimes it treats this one as a weight. So you want to put it together. We proved it in the case like without anything. So that's why it's weird. But let's define it as in the book. So forget what I said before. Define the excitation as this with the minus the threshold. And so then when I evaluate the function, the activation function of threshold theta k, I take the weighted function and it's the same as doing the sine of ek. So it's more compact. But you can see that it's the same thing. It's a matter of what I call ek. It's the definition of ek. So either I put it without theta k or with. Yeah. Let's use this one. So ek is the weighted sum minus the theta k. It's reasonable because when we do extended network, this becomes a weight. So it's pushed in the sum. So I just want to do, when I evaluate if something passes the threshold or not, I just put ek inside that here. And this becomes x prime k. That's how I update. So yeah, let's remember that. So I'm update. I told you that I update xk in the proof. At least I'm just I took a vector. I said this is the energy function. I update xk just one unit, so I take a vector that is equal to the other one for every one except the units that I updated. Note that x prime k is equal to sgn xk or ek that is equal to f or yes f theta k of the weight itself. Okay, what does it mean? What does this mean? I'm updating xk. So xk before was either 1 or minus 1. If I updated it, it means that it's not the same. So it means that if it was a 1, it will become a minus 1. If it was a minus 1, it will become a 1. So that's why x prime k means minus f3. I changed the sign because I updated. If I didn't, the energy would stay the same. So now, as we did for the bumps, we want to do the energy of x minus the energy of x prime. And do many, many computations until we cry. And then we will see what's going on. So let's do that. Not not a big deal. We're just gonna use the hypothesis that we have on the W. That's why they were important. We saw last time that intuitively they were fine. Yes. Again, I want to show that the energy has decreased. So if I do the difference between the energy before and the energy now, I want this to be part of my dreams, okay? So we do all the computations. I use the formula that I used before, but for both of them. So I put I comma j, but it's two sums, sum over I, sum over j, just to be more compact because there's a lot of stuff going on. xi, xj plus sum and I do minus whatever else in x prime, so the energy now, so I have plus just using the definition of the energy. Thresholds are the same. Now, I want to use what I know. So, in particular, I want to take out the case in which I and j are equal to k and separate all the rest, because I know that all the coordinates in x prime are equal to the ones in x, so something should go away. To do that, I split. The first, let's consider first this. Phi different from k and j different from k. Then I take out of the sum the case in which I is equal to k and j is equal to k. So I have minus somehow. All this is equal to this point. I put here that j, so here corresponds to the case that j is equal to k. And then I also do I equal to k. Here by symmetry, wkj is equal to wjk. xk, xj in the case for I equal to k. This is just the first term. Now, I do the same for this one. Take out the case k equal, I equal to k and do I different, like I different from k. So. And then I put what's the same. Out, I have the term theta k, x k, the only term for k, I equals to k. And yes, I do the same for these two. So good luck. Since they're different than k, these two are actually equal to xi, xj. Only the x prime vector is equal to the x vector for every coordinate but xk. So I do again the sum when j is equal to k and the sum when I is equal to k. This is when j is equal to k. Because I have to take it out from this. I'm just doing the same thing, so it's not too big deal. This is equal to xi. And this is x k prime. I have to do it also for the case of I equal to k. This is equal to wjk by symmetry, and this is equal to xj. This. Then I split again the sum of the last term. Theta I xi for I different. Here did I say that j is this is equal to x I third minus theta k x prime k. Now, why did I do all this? Let's start looking at the terms. This one and this one are the same. Complete opposite sign, so I take them away. Similarly, you consider the theta I term, this one, and this one are the same, but on the opposite sign. This is plus and this is minus. It's slowly going. So what is left? That's the question. One needs to see that this sum and this sum are the same sum by seeing. So I can just sum them together because it's alpha of something plus minus a half of something that is equal. So I can just put them together. Same with those two. This guy and this guy. And put them together. So when I'm left is that I put those two together, and I have those tiny terms in the end. So it's not pretty bad. Let's write it down here, maybe, or first line. Let's write it here. So I sum the first two terms, and I choose I as my index. So I, that goes from 1 to n of wik xi xk. Then I put the other two big blocks that I fused together. I goes from 1 to n of what? Wik xi prime xk prime. Note that this is xk. Yeah, not n. Let's take just the terms that were remain single, theta k, xk, and these other one minus theta k. So we're just left with this. What do? We note that in this sum, I can put I different than k and I different than k, even though it wasn't an assumption, because of the zero diagonal. So if I put I equal to k, here I have WKK. The WKK is 0 because I have 0 diagonal. So this implies that I can put I different than k. Since I is different than k, I can remove the apostrophe here. Because for all the i's different than k, the x prime is equal to the x. So that's all I'm left. It's not so bad. Especially if I can put those sums together, and these terms is similar and just this one is different, so I can compactify a little bit. So let's leave here the sum. And I can't. That's the video. There is always the video, thank God. Are there questions online?
Nope.
So, now I want to put this up here and clean it a little bit. Let's do it. Believe me if I do this. From these two, I come up with this. It's okay. And from these two, I just take the k, theta k out. It's not so bad. It's the same as we did with the BAM. But now I have the same term. This. So I can just write that the energy is minus xk minus x prime k, and in the parentheses I put 5 and yeah, this minus was just in front of this, so here I have a minus. Okay. Believe me, it's true. But now, let's take away. What do I get? This is the excitation according to the book. Excitation. This is equal this big part. So it's not so bad. I have xk minus xk prime times the excitation. But I told you that xk prime just is minus xk because I changed the sign of 1 unit. So I have minus 2 xk ek. Not so bad, indeed. What is going on? So when I update, I told you that the updates go working this way as well. Xk prime was the sign of the excitation. Because was this. How do I update? With my updating function. Activation of threshold theta k. So if xk prime has a different sign from xk because I changed it, it means that also ek, that is, sorry, xk prime is the sign of ek. So it means that also ek has a different sign from xk. ek is an excitation, so it's not a -1 and a 1. I do the sine function and then I obtain a -1 and a 1. But if this has a different sign than xk, also this has a different sign of xk. It's just that xk is a -1 and a 1, and this is a number. But its sign is the opposite of xk. So what is going on? I have two things that have opposite sign. So this is the product of these are sign as negative sign. But minus times minus is plus, so this is positive. So the energy is decreasing. So we proved what we want, that the energy, the difference between the energy before and the energy after is positive. So the energy has strictly decreased after one update. Why does the energy not go to minus infinity? Because I have a finite set of states and I can calculate the mean. So it doesn't go to minus infinity, and this thing converges. So everything is nice. Intuitively, we saw that things were going down to stable states, but actually it's moving. So what's the tricky question? Because last time I told you that symmetry and zero diagonal, that are the only hypotheses that we use in all this graph. The only, like, I showed that I showed the update of xk, symmetry, and zero diagonal to do the steps. But last time I told you that symmetry and zero diagonal were not sufficient, like were necessary but not sufficient to have convergence. So where is the trick in this thing? So if you see the proposition, I say eventually reaches the state of a stable state of local minima for the energy. But can I be evil and choose a pathological path? So let's come back to our this. I told you that in the state, I think 1 minus 1 minus 1, the one on the upper. If I say x1, I will stay there. It's not a stable state, because if I say x2, x3, I go away. Let's hope it's correct what I'm saying. But you get the idea, right? Imagine that I go there for some reason, and then I just start saying, okay, my update is x1. It's random, so it can be x1. It can be a sequence of x1. That thing will never converge to a stable state. It will always stay there, because I update just x1, and x1 lets me stay there. So the concept of convergence in Hopfield network is like probabilistic in some sense, because like the probability of not reaching a stable state goes to 0 as the iteration goes on. So the probability of picking a pathological path goes to 0. So I can pick a pathological path, but it's unlikely. If I do random updates to pick the sequence x1, 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 it will not happen the more I iterate. So that's the problem. And that's why we with that probability we will converge to stable state. But that's purely thing, That's why I say eventually reaches a stable state. Yeah, caveat is just like pay attention, but enough. Yeah. I wanted to show you this. I don't know if I have time to do all I want. So maybe I will show. This is a different proof than this graph that I told you before. It's a bit cooler. So I want to tell you about it. Let's hope we have time, or maybe I will do this first thing next time. So yeah, let's do before the equivalence between Hopfield network and perceptron learning. So as you saw for the OR problem, the equation is that whenever I have a Hopfield network, I can convert it to a perceptron in which the stable states of the Hopfield network, since there are stable states, since we proved that it converges, correspond to the input outputs of the perceptron. So this thing can be proved, like you can show that given a Hopfield network, I can construct a perceptron. And this is cool because for perceptrons, we have a way with perceptron learning to update the weights. was not the best way. There's different ways, but we saw a way of updating the weights in order to make it converge. And here we want a way to find the weights of a Hopfield network, but using the algorithm that we did for perceptron. So we need to find a way of passing from one to the other, basically. So we need to do a few special. This is like the final result, but like it takes some time to get it to it. So let's do it. So we want to use the perceptron learning algorithm to update the weights of a Hopfield network. So we want to treat a Hopfield network as a perceptron. We have to specify a few things before doing that. Also asking the size of that thing, because it's not clear. So we have to remember that in perceptrons we use the zeros and ones, whereas in Hopfield we use minus ones and ones. Relation function was Heaviside step. And theta I, here we use exact theta I. I don't know. There's a way of passing from one to the other. It's not what is going to hurt us about the conversion process. Let's move on. Imagine I have a Hopfield network of n units. So that's 1 plus 3. Weight matrix n times n. Let's write the matrix down. These are zeros on the diagonal. This is the same thing. And here I have 1, 1, 2, 1, 3, 1, and how many different coefficients I have inside this thing? So what's the cardinality of this line? You have to do the sum of what? The first line you have n minus 1. And you have the plus n minus 2. Plus, and in this last one you have just 1. N minus 2. Yes, n minus 1 n. There is just one guy. It's left. When you're summing starting from n minus 1, because you know the first one is 0, plus 1. This thing did like Gauss sum code in primary school, or I don't know. There's proof of whenever. I'm not gonna tell you why this is true. This one is true. This is equal to n minus 1 divided by 2. Trust me, if you don't trust me, go find it somewhere. This is true. So we have n times n minus 1 different coefficients in this machine. We have the threshold vector on the Hopfield network. So my idea is that I have a Hopfield network. I want to construct a perceptron with all I have, with all the data I have. What do I have? This. Okay. So I want to find a way of checking whether I updated or not a unit. Why? Because imagine that x, let's call x is a state of my Hopfield network. Imagine if it was a stable state. A stable state is a state such that whenever I update one of its units, it stays the same. So I want to find a way of checking whether I didn't update the state. Because before we were checking, like, you remember in the perceptron learning algorithm, we were checking scalar products. So I was kind of something that is the weight vector that I have to find. So something that includes the thresholds and the weights, that in this case are this number plus n. This number for the weights and this number for the thresholds. So I want to write a threshold vector, a weight vector that my perceptron learning needs to find. And I also want conditions such that you remember that we had those points that had to be classified positive and negative. I want the analogous, but that checks whether a state, it is a stable state or not. If it's a stable state, so if, for example, it has great inequality, then it means it hasn't been updated. So that's the analogous I want to do. Like I want some vectors, some auxiliary vectors starting from the state vector that tell me whether something is a stable state or not, checking inequalities. So in this way, I have a perceptron such that when I apply perceptron learning, it finds me the stable states of the object. Let's try to do that. So if I consider the unit 1, having a stable state means that the unit 1 is not updated. So this is the sign of the first coordinate in the state vector. And I write this, let's hope. I just write E1. Because when I update x1, xy prime is the sign of the excitation. Which means that is the sign of 0. Let's write the excitation here instead. Sign of x1 times what? 0 because nothing comes from itself. Plus x2 w12 plus x3 w13, etc. Plus xn w1n minus theta 1. So if the sign of my vector before is the same as its excitation, it means I didn't update it. If it was a -1, it would stay -1. If it was 1, it would stay 1. If they are different, it means I have updated. So you have to believe me when I say that saying that this is greater than 0 means I have not updated the unit x1 with all these coefficients, because that's what goes to x1 plus minus the threshold of x1. Okay. And I do the same for all the units. So I consider unit 2. I do the sign of x2 times the excitation 2. So sign of x2 now it's x1 w21 plus 0 plus x3 w23, etc. etc. minus theta 2. And I want this to be greater than 0, etc. Unit n, the sign of xn en greater than 0. Okay. So if all those things are greater than 0, means I've not updated. So how many weights do we have overall? I told you that I have this quantity plus n. So the sum of all the parameters that I have in my problem, in my Hopfield network, that I want them to be the weight vector of my perceptron. If I do the sum between those two, I obtain the sum of the first n integers. So I obtain n, and it's 1. So I have this amount of weights, and actually this will be the size of my perceptron. If I start from a Hopfield network of dimension n, I get an equivalent perceptron of size this. You can see from there. All the weights and thresholds all together become like stuff coming from the left side. So the new weight vector it's not shocking. I just put it's a vector that has this size, and I put together all the weights in the matrix and all the thresholds, but with minus. So I have 1, 2, 1, 3. This is the first line of the matrix. This is n minus 1. Then I have the second line of the matrix. That has n minus 2 terms. That goes to 4 w to n, not n minus 2. Then I have w, the only one in the last coefficient I can get. And then I have all the threshold. Is it just 1? And then I have all the threshold minus theta 1 minus theta n. This is my weight vector. Since I have n times n plus 1 divided by 2 weights, I need to have vectors of the same size as input vector. Because imagine that is your perceptron, you have to put x1, x2, etc. for how many weights you have. So how do I define those vectors? So my vectors will be of that size, but the vectors, like the PIs, on which I check positivity, for example, in perceptron learning, where we have 1 belongs to P, will be those vectors. Here. Where x2, x3 are the ones coming from the Hopfield network. And then in the last ones, I put 1 on this. Then I put zeros again. This is n. So I put x's for just the first stop, and I call this zeta 1. Then I put 1 here. Why do I do that? Because I want this to be the scalar product between zeta 1 and w. This thing, the excitation 1, is the scalar product between zeta 1 and w. This I want this to be zeta 2 times w. So I can check positivity times the sign. But the sign is a constant because it's given with the output network. What we're trying to do is to modify the weights, but the inputs are fixed. So I have scalar products that I check for the sign as in perceptron learn. And those vectors, zeta 1, etc., are like the PIs, for example, in the exercise you got in perceptron. So I got zeta 2. This one. Why did I put x1? Because here I have x1 times w2 1. So I want this to be multiplied by this. So this is the n minus 1 part, and this was the n minus part, etc. And you do in the last n, you put zeros, and then in the last n, you put 0, 1, 0, and 1, 0. So you can check that this, the scalar product between these two gives me the excitation too. Or just find a way of putting the axis. Yes.
Quick question: what is the sub-index there in this? Yeah, this one. 1 2.
2, 4.
Okay.
That is 2, 3, 2, 4. If you take the matrix W, this is 0. This is 1, W, sorry, 1, 2. This is where it's supposed to be W2, 2, but I have 0. And then this is W2, 3, W3, 2, oh, sorry, 2, 4. It's the second line of the weight matrix. Like if you write all the coordinates of the weight matrix, you see that these are the, I take that, I don't know what to say, but like, yeah. This is my matrix. I have zeros here, and I have lines here. I take all the weights in this first line and I put them here. I take the weights in the second line and I put them here, etc. And the last one is just 1, and I put it here. All this, like, it looks like very chaotic, but it's just a way of finding input vectors such that their scalar product with this big weight vector checks for being a stable state. So it's kind of putting the stuff from the Hopfield network in order to have a problem that is posed as a perceptron learning. And this is zeta n. I put x1 in the n position, and minus 1, sorry, n minus 1. Put 0, x2 in the n minus 2 position. All zeros. And then I put in the n. And you can see that checking whether any unit was updated, let me write it like properly, corresponds to checking scalar products. Like these data ends are really, like, they're called auxiliary vectors, but they're really what they were the PIs in the perceptron learning method. We saw that like having positive and negative, you could like bring the negative on the positive side, and it was everything positive was worked the same way. But yeah, we just check for positivity in this one. So checking if I updated unit 1 corresponds to doing S the sine of x1 zeta 1 times b greater than 0, sorry, w greater than 0, unit 1, unit 2, x2 zeta 2, and so on. So I can apply perceptron learning and find the weights and thresholds actually from my that. And that's actually how they find the weights for the XOR. Like you remember the XOR, like as a Hopfield network, you can find its weights, converting it into an equivalent perceptron, and then you find the weights and then you put them back with this transformation. How much time do we have? 5 minutes? Yeah, I'm just gonna tell you the idea of the other proof because I think it's cool. It's cooler than what I just said. So this is unrelated to equivalence between perceptual learning and Hopfield. This is not clear. So I proved that we were going towards minimum for the energy. There is another way of doing that rather than just writing the energies and updating one and see whether the difference is positive. That is this. So let me write an example so you can see how fun this is. So the idea is that I have my Hopfield network My Hopfield network is a series of nodes. It's a series, I mean, it's not a series, like, it's a set of nodes with edges. And each of these nodes can be -1 or 1, and I don't know. So, let me make an example so it's kind of easier. Yeah. So, imagine you have this network with thresholds vector equal to 0. So it's a simple example, but x1, this is x2, this is x3, and I put these weights. 1, a half, and 3. Okay. Imagine I'm in the state -1, 1, 1. So this is -1 and those two are 1. The idea is that I put a line between I put all together the ones and all together the -1. So this is -1s and these are two are 1, so the line is here. These are the negatives and these are the positives. And like we call it, the attraction inside is each political party, like this, as this attraction. And if there were two here, there would be something, whatever this dimension is. But then you have also like the sum of the attraction between parties, And the idea is that what an Hopfield network does while it computes is that tries to increase the inside attractions and decrease the ones that cross the line. I can show you that, for example, if I do an iteration is right. I think you can say I update x3. So do I update x3 from I do the sign of what? 1 times -1, so -1, and 1 times a half. Yes. This is clearly negative. So I'm bringing this guy to this side. This is minus. So what the network has done, okay, instead of bringing this guy on this side, I just like change the line. The line now is here. And you see that before the weights that were on the line were 1 and 2, and now they're 2.5, so it's less. You can prove actually writing the excitations that if you write all together, like just the weighted sum that crosses the line and the weighted sum that are inside the parties, these weights tend to decrease. If you update again, the other update will give you this. If you update if you update x1, I'm doing random updates because that's how it works. The new line will be like this. That is smaller again. This is sorry, and this is now I think negative and this is positive. So it's also the problem of finding the minimal cut of a flow. Like this is something known in graph theory. Like I'm finding the cut that this is you can show that the proof of like convergence is equivalent of finding a minimal cut, reducing the flow that of the edges that cross the cut. Yeah, this is the idea. I think it's cool because it works for every dimension. Like you can write really like this is an example, but you can write the weight what happens on this side and on the other side. If you split the sum inside the excitation, U1 was the sum of the weights, you say the sum of the weights that are positive, and with the weights multiplying the positive and the weights multiplying the negative, and it works out. So I think it's a cooler proof than the other idea, but that's where we are. So yeah, sorry for being late. I'll see you on Monday. If you have any questions, do you have any questions? So I'll see you on Monday. A nice weekend.